Good afternoon, everyone. Good afternoon. So I would like to welcome you all to yet another one of our Feynman lectures that is hosted by the Physics Society of St. Stephen's College. Today it is our honor to welcome Dr. Rahul Siddharthan. He is a researcher from Institute of Mathematical Sciences from Chennai. So let's welcome him with a round of applause. Dr. Siddharthan is a leading researcher in computational biology and bioinformatics, whose works combine physics, mathematics, and computer science to study gene regulations, evolution, chromatin structure, as well as clinical outcomes. Today he will be delivering a lecture on a gentle introduction to Markov Chain Monte Carlo sampling. This method is a cornerstone of modern computational physics and statistics, with applications ranging from Bayesian inference to simulations in high-energy physics, and even extending to diverse fields like biology and finance. Today we are fortunate to have him here with us, and I warmly welcome Dr. Siddharthan to deliver his lecture. A quick reminder before the lecture begins to kindly put your phones into silent. Thank you.
Thanks very much, everybody, and I've never actually done this before, as in talk about this topic so I used to sit somewhere there 31 years ago, and anyway, so I thought to keep it as informal as possible, and please ask questions as and when you have them. That will work best. So before we start, I just wanted to get an estimate, which year are you all in? All years, first, second, third? All. Okay. And how many of you have done any statistical mechanics? I believe there is a course in the third year, but you probably just started it, and the rest of you would not have done it, right? But you know basics of heat and thermodynamics, what at least high school level. So let's ask a simple question. When you say something is hot, there are two connected notions, like a glass of water. You add energy to it by microwave or putting it on a heater, whatever, it gets warmer. So there is a notion of heat and there is a notion of temperature. Right? So how are these two connected? Are they the same thing? Are they different, heat and temperature? Or let's say it's not heat, let's say energy. You have added energy to the water by putting it on the stove or whatever, and its temperature has increased. So how are these concepts connected? So you'll probably do that in your thermodynamics course and in your statistical mechanics course. And in classical thermodynamics, going back to the 18th, 19th century, temperature was kind of defined somewhat arbitrarily as a way to decide whether heat flows from one body to another. Supposing you have two objects, I'm thinking of how to present this also, because as I said, I haven't done. So you have a hot object and you have a cold object, and you put them next to each other. And when you say hot, let's loosely think about temperature. So this has a higher temperature, this has a lower temperature, we have here different temperature. So what happens? The hot object will become cooler and the cool object will become hotter. So that's because heat flows from the hotter object to the colder object, right? So heat does not flow the other way around. So there are two famous laws of thermodynamics. There's something called the first law of thermodynamics, which is basically a statement of conservation of energy. So it's basically saying that, it's basically saying that heat is conserved in some sense. But you conserve energy equally by moving energy from the cold object to the hot object. Supposing you took 10 or 20 joules from the cold object and it becomes colder and this becomes hotter, that conserves energy, and yet that does not happen. And why does that not happen? So that is the second law of thermodynamics. The second law has many different statements over the years, but one of the statements is that heat cannot by itself move from a colder body to a hotter body. So of course it can move, but you have to put in some work to do it. You can have a refrigerator or an AC or whatever that can move heat from a colder place to a hotter place. But all by itself that cannot happen. That is one possible statement. There are other statements of the second law. One of them is that the entropy of an isolated system always increases. Now, what is entropy? Has anyone come across the term entropy? So, entropy again was something that was defined in one way in the early 19th century, and then a different definition came up later. So, there is classical thermodynamics, and then there is statistical mechanics, which was invented as a way to explain classical thermodynamics, so we think of it that way. So heat is an intuitive object, but heat is related to energy. So if you have a hot object, it has more energy in it, which you have put into it somehow. Temperature is not the same thing. You could have a small hot, let's say, small hot box and a big cold bath. In terms of energy, this will probably have more energy than this. But that's not the reason heat goes from this to this. Heat is still going in this direction because the temperature is higher here and lower here. So classically, people just invented temperature as a way to decide in which way the heat will flow. So when two things are in thermodynamic equilibrium, that means they have the same temperature and heat will not flow between them. So one way to, so they found that, for example, gases typically, so they came across this concept of temperature, then they find that if you increase the temperature of a gas, adding heat to it, it expands. So that's one way you could, and then it need not be a gas, it could be a liquid like mercury. If you heat it, it expands. So they came across the idea of calibrating temperature according to these things. So you can make something like a thermometer. And so, for example, they decided that boiling water, I think Fahrenheit wanted the human body to be 100, and but he got it slightly wrong, so 100 of it excess, and he wanted the coldest temperature known at that time to be 0. So that's like minus 32. And so then they invented ways to, like thermometers that check the temperature. How does a thermometer work? This is a sort of an object here. It is a small bulb with a mercury in it, let's say. And if it heats up, the mercury expands and goes up. If it cools down, it goes down. And if you want to measure the temperature of an object, like let's say this is a bath, you put the thermometer in there, and if the thermometer was initially hotter, heat will flow out. If it was initially colder, heat will flow in. But the hypothesis is that the thermometer is much smaller than the system. So if it's your clinical thermometer and you put it in your mouth, it will initially, let's say the thermometer is like 30 degrees, but your mouth is at 37 degrees. So the thermometer will take heat out of your body and expand. That way, your body of course cools, but that's such a negligible amount that you ignore that. And only your body is generating some energy. So that's the idea, that you use this kind of measuring device to determine what is temperature. And then a guy called Clausius came up with the concept of entropy, and so he framed the second law. So the entropy is defined in a different way in classical thermodynamics, so I won't get into that. What I want to talk about is statistical mechanics today, and the application of sampling in studying such systems and then other applications. So let's get back to the ideal gas. So actually, since I want to get back into sampling, I think I'll just make a bunch of statements about prove anything. So the idea is something like this. A gas is a complicated object, but it has molecules that are moving around, and if you actually measure the gas, supposing now this is a box, there are gas molecules inside the box, and these molecules are moving around at different speeds and different velocities. And it could be some of them are moving slower, some of them are moving faster, but there's some distribution of velocities. And people kind of understood this at that time. And if you heat the gas, you are adding energy to the gas. So it makes sense to think that these molecules are moving around faster. And if you cool it down, the molecules are moving around slower. And the other thing that you see about the gas is that it fills up the box, right? If you could have, imagine a scenario where you have some small box here where all the gas is trapped, some sort of partition, and then you remove the partition, and then the gas fills the whole box. But then you never see the gas going back into the small thing by itself. Whereas if you look at the laws of classical mechanics, Newton's laws, they are time reversible. That means that if you see a motion going in one direction and you play time backwards, what you see is equally plausible. If you see a pendulum going this way and you play the tape backwards and the pendulum goes this way, it's equally plausible. But in a large system like this, technically, if you were to play the clock backwards, you will see all these molecules that went out going back, bumping against each other and everything, and they will finally come back in here. And that is a completely allowed motion by Newton's laws. There is nothing that forbids it from doing that. It's not breaking any of Newton's laws when you do that. But you will never see that happening here, right? So what's the reason for that? Anybody? Why do you see? Yeah.
Because entropy means that information is lost. So they
Okay.
never come back to the same.
Okay, so you use the word information.
Yeah.
What do you mean by information?
Information of the position, the velocity. So courtesy of the large number of those molecules, if they exceed a certain threshold, they will never return to the same state.
Yeah, that's a good starting point. Yes, so you can also put it by saying that you can never describe this gas by describing the velocities of each individual gas molecules. There is no way you can ever have that information. So you have to describe the gas by some kind of macroscopic picture, and so you will deal with variables like pressure, volume, temperature. Those are the things you use for an ideal gas. And you could also think of at the micro level the velocity distribution. So you could there is something called the Maxwell distribution for velocities of ideal gas particles. So you'll find that it's kind of peaks somewhere and it goes down, but you can't describe every one of tangent the molecules in detail. So what you had at the beginning is the information that these guys are in the small volume. And another way to put it is, so the way to think about it is how many, so there are two words that they use in statistical mechanics, a macro state and a micro state. And a micro state is describing the velocity of every particle in minute detail, and a macro state is just describing the big picture, loosely speaking. So then you can ask how many microstates could possibly belong to a macro state. So now your macro state is the broad description, And this, where everything is in a small corner, is actually a plausible microstate. There is some state of the system where, because that's how it started, it could go back there. So the question is, how probable is it that it will go back there? And that's kind of the reason for the arrow of time, as they say, that it goes towards increasing disorder because there are just more disordered states and fewer ordered states. So statistical mechanics is a way of formalizing this kind of a picture, dealing with systems in this kind of large sense. So with that sort of loose introduction, let's move. So gases are complicated. They, velocities are like continuous variables, and they could have so let's look at a simpler problem where you have a collection of objects so these, let's say this is a sort of toy picture where you have just 10 boxes. And this is a system where you could put in a particle. You are not worried about the particle moving around in the box, that's not what you care about. But every box has an energy associated with it. Let's say you just have one particle. So you have one particle, and that particle can be in any one of these boxes. And but it can jump around. You are this system is existing at some temperature, and so to make it concrete, these things could be like energy states of a molecule. So the molecule could be excited into different states and so on. So you actually have physical systems where you have discrete energy levels. So just think of when you observe the particle, it might have some probability of being in one of these n boxes. How do you estimate that probability? That's given by, and let's say this is an increasing order. So E1 is the lowest energy, E sub n is the highest energy. So as we discussed, if you heat up a system, you're adding energy to it, and intuitively you're increasing the temperature. So you would think that increasing the temperature of the system is sending the particle towards the highest energy state. Whereas if you cool the system, it will go towards the lowest energy state. And that part is actually correct, that if you cool the system to absolute zero, the particle will stay in the lowest energy state. But as you increase the temperature, there is no temperature where it stays in the highest energy state. So temperature is actually not linked to energy in that sense. It's linked to, okay, so let's just write down the formula that Boltzmann gave. It's called the Boltzmann probability. Probability of the particle is equal to e to the power minus e sub n by k t divided by a normalizing factor because it's a partition function. So what is this? It's the nth box. Let's say this is e sub n, and T is the temperature, and K is a constant that is called Boltzmann's constant, but we can choose units where it is 1. So you can think of it as just a conversion between the units of temperature and the units of energy. So and Z is the normalization, so the particle has to be somewhere. So these probabilities have to sum to 1. So Z is just the sum of all of these guys. So that looks very simple, and you will derive this in your earlier course, I guess. I'm not going to derive it, but it can be derived quite simply. What you notice is that at low temperature, this object So what does these e to the minus e's look like? So what does the exponential function look like? It is a decaying function, right? So at 0, and the exponential is always positive. So it's always negative because this part is always positive. But that doesn't actually matter. As e increases, this probability decreases. Also, as t decreases, this decreases, right? Because as t decreases, this whole number increases. So the exponential function looks like this. It falls off this way and it rises very rapidly that way. If your temperature is very low, and let's say you have some energy states like this. So this is, let's say this is e to the minus x, but as and this is a factor that's multiplying 1 by kt. So if t is small, so it's conventional to write beta for 1 by kt. Let's just write it that way. So beta is called the inverse temperature, it's just 1 divided by kt. So small temperature means large beta. Now supposing your temperature is small, so beta is large, that means this function will fall off very sharply, so it will be more like maybe this. And that means almost all of your probability will be in your first energy level, and the other ones will be very, very unlikely. So as you go to 0 temperature, your system will go towards the lowest energy state. It's called the ground state. But if you do the opposite, if you increase the temperature, that means you're decreasing beta. So as beta goes smaller and smaller, these become almost the same size. You never get to a position where the last one is the most probable. Instead of high temperature, all of these are equally probable. So that's kind of the basic idea in StatMech, that for any system you have a bunch of possible energy states it can be in, and the probability of being in any particular energy state is given by this Boltzmann factor. So please stop me if you have any questions about any of these things. And so with that quick introduction, and you can use this formalism to deal with ideal gases and so on, and the way you do that typically is for ideal gas you don't have discrete states, you have continuous, you can have any value of energy. But you can still, and the set of possible states it can be in is called phase space. But you can still divide that phase space into boxes, so to speak, of the equal energy, and then you can do this kind of calculation, and you can recover the properties of an ideal gas from that. So I'm not going to go into that today. But you can use the same kind of formalism to study spin systems, magnetism, and so on. That's one of the earliest examples of that. So what do you know about magnets? How do magnets work? Oh yeah, yeah.
There are like large number of small magnetic dipoles and they are aligned.
And what are these dipoles? Where do they come from?
Basically.
Yeah.
Electrons.
Yeah, so the magnetic moment of the electron. So there are different kinds of magnets. You know, ferromagnets are the permanent magnets we talk about. But you know about and then there's diamagnetism and paramagnetism and antiferromagnetism. Antiferromagnets are actually much more common in nature, but they won't. So let's just give a model of a magnet based on what you say. So, so you're right. So all substances are made up of atoms. Sometimes it's a pure substance like pure iron is only made up of iron atoms and almost nothing else. Sometimes it's a much more complicated compound, but some of those constituents might have magnetic moments which can come either from the electrons or the nucleus for heavier atoms. But electronic magnetism is more important case. So let's say you have a square. So most substances we deal with are crystals. That means their atoms are arranged in a regular lattice, like a square lattice. Let's imagine it's a square lattice. Or maybe to make it simpler, let's imagine it's a one-dimensional lattice. So it's just a one-dimensional system. So these are all atoms. And each atom has a small magnet. And this magnet in principle could point in any direction, right? So it's just it could point out of the board, whatever it is. And now to study a system like this, a system could be in many different states depending on how these magnets are pointing. So they could all be pointing in the same direction, they could all be pointing in different directions. But each state has an energy associated with it. And that energy depends on how these small magnets are interacting. So how do magnets interact? Suppose you have two magnets, what is the interaction between them? Is it
magnetic fields.
Yeah, so do you know how it goes roughly?
Yeah, UV cos theta.
Sorry?
Like UV cos theta.
So, and is it short range or long range? Like will this guy interact with this guy, for example?
Usually short range.
So it actually goes, like magnetic dipole interaction goes like 1 by r cube. It's like mu1 dot mu2 by r cube, something like that. That's the, so you can, so in physics you normally, when you have a complicated system, you try to simplify it. And if you're trying to analyze a phenomenon like magnetism, before getting to a real magnet like, I don't know, whatever, you think of a model system that might give you the same possibilities. It might exhibit the same features as the real magnet, and you see whether you can solve that system. So one example of a model system is the Ising model. It was the first example of a model magnet. It goes back to the 1920s. Ising was a PhD student and this was his thesis, and in fact he specifically did the one-dimensional Ising model. So the model is simply this, that you have a lattice, and in this case it will be a one-dimensional lattice, and the lattice sides steps from them onto n sides, and the n side has a small magnet which we'll call S sub I. But we want to simplify. A real magnet is a vector. It can point in any direction. But this says we are going to take it to be a scalar, meaning it can only be up or down. And that actually happens in a lot of materials, that the magnetic moment is constrained to be in a particular direction. So it's not such a bad approximation. So each side has a variable associated which is S sub I, which we assume can be plus or minus 1. So again, these electronic orbital magnetism has a fixed value, it doesn't change. Its direction can change, but we are assuming that because of whatever reasons, direction is only up or down, it doesn't go anywhere else. So this is the system, and the interaction between two successive spins is simply going to be there. So I'll write down what the energy function is. I'm going to call it H for the reasons I will mention, but let's say H is equal to J times summation from I is equal to 1 to n minus 1 for the n sides will be S sub I times S sub I plus 1. So these S's are the spins, and each term in the sum is a pairwise interaction. So the first term I is equal to 1 says this spin times this spin, and then there's this spin times this spin, and so on. So there are two possibilities here. J can be positive or negative. The value of J doesn't really matter. But if J is negative, that means that the energy will be minimized. So if these two spins are pointing in the same direction, their product is 1. If they're pointing in opposite directions, their product is minus 1. Right? And you, if J is positive, that means that these spins will have a lower energy if they point oppositely. If J is negative, then they will have a lower energy if they point in the same direction. So you are all with me so far. So this is called the Ising model of a magnet. So the assumptions are that each spin is interacting only with its neighbor, and that pairwise interaction with the spin with its neighbor is just the simple product of the values of the spin, plus one factor minus one and so on. So for example, you could have let's say this is the configuration, this one. So I'm going to represent plus 1 by R and minus 1 by tau. And let's say this is my configuration. Let's say probably 7 spins. So it is going to be, if it is going to be J times plus 1 minus 1, which is 0. So the total energy in this configuration is going to be 0, right? The sum of all of these. Whereas if I had a configuration like this, then the total energy will be 4 times J. So J, if it is, let's say J is positive, then this will be a high energy state. But if J is negative, this will be a low energy state. So I called this the energy function. It is also widely called the Hamiltonian. That's why I use the letter H here. So in classical mechanics, the Hamiltonian is a function with which you can describe the system, but it evaluates to the energy of a system or conservative system, and you use the variables position and momentum typically to write it. In quantum mechanics, it turns out the Hamiltonian has a very fundamental role in describing the system. So this is actually a classical system, it's not a quantum system. These are just numbers and they're just playing with them. There are models of magnets which are quantum mechanical, which we will talk about. So it's a very, very simple model. So now we have a system of a model of a magnet, one-dimensional magnet, and we can calculate the energy of it using this formula. So now what do we do with that? So what do we want to know about a magnet? We want to, for example, know whether there is any total magnetization. So let's say, so what is the total magnetization? In this case, it's just proportional to the sum of all these spins, right? So in this case, it is plus 4. So 6 of them are pointing up and 1 is pointing down. So okay, so the magnetization, so the energy is plus 4, the magnetization is plus 5, which is the sum of the spins. In the other example that I gave, which looked like this, and so this had 0 energy, but the magnetization is still plus 3. So for any given state, you can easily calculate the magnetization. But again, we are talking about microstates here. We are telling each spin is up or down, and that got at 7 spins here, but a real magnet will have 10 to the power 23 spins, and you can't be analyzing that in any sensible way. So what can you do? Supposing you don't have 10 to the power 23 spins, you also don't have just 7 spins, but you have a large number. Let's say you have 100 spins or 1,000 spins. Now you can imagine that this is something you can simulate on a computer, and then you can see how it behaves. But before doing that, you want to know how probable is any particular state. So now we are going to talk about the configuration of the system. I'll call it C for configuration. Is just the collection of values of these spins. So this is a microstate. So a configuration is a microstate of the system. It's just assigning values of all these spins. And the energy of that configuration is not about there. But now you have how many possible configurations are there with n spins? You have each spin can take 2 values, and you have n of them. So you have 2 to the power n configurations. So if you have 10 spins, you'll have more than 1,000 configurations, and if you have 20 spins, you'll have more than 1 million, and so on. So it just grows very fast. So if you have like 1,000 spins, you simply cannot explore all possible states of the spin. But what you want to the things that you want to calculate are like the average magnetization. Any particular state has a magnetization, but even at high temperature, you could have all spins up or all spins down or whatever, but that's not a very probable configuration. So what is how do you say whether a configuration is probable or not? So that you can use Boltzmann's formula, which is what we just talked about. So the probability of a configuration is simply going to be e to the energy of the configuration divided by kT, and the whole divided by the partition constant Z. So each configuration has some energy value. So let's take for completeness J is negative, J is equal to -1. So let's just say H is equal to minus of this. So we are talking about a phenomenon. Then the energy of this configuration the energy of this is equal to 0. That's what we just calculated. Plus or minus 1 minus 1. Whereas the energy of this configuration, when everything is pointing up, is going to be 1. So each of these is 1, but the whole is multiplied by -1 because of J is equal to -1. So there are 6 pairs, so it's going to be -6. And on the other hand, E of this is going to be +6. So for the choice J is equal to -1, this is the lowest energy, this is the highest energy. If I put J is equal to +1, it will be the other way around, this will be the lowest energy. So, but typically it will not be in any of these configurations, it will be in some different configurations. So that's the idea of statistical mechanics, that you have a larger description of the system and you cannot describe it via these microstates. Instead, so I asked you what would be the magnetization of the system. So the magnetization of a configuration, let's say it is just equal to the sum of the spins. Find some constant, but so the magnetization of this plus 7, this would be because it's an odd number, you get a this will be +1, and for this one it will be B. And you could have a state where all of them are down there, it will be -7. So each state has a magnetization, but that's not what you're interested in. You don't know the state of the system, but you do know the temperature. So you want to get the average magnetization, that's the expected magnetization at that temperature. And the formula for that would be you have to average this object over all possible states. So commonly we represent averages by angle brackets or by the expectation. Let's use angle bracket. The magnetization averaged over all configurations is equal to the sum over all possible configurations of m sub c, which is the magnetization given by this formula, times e to the minus e sub c by kt, which is this guy divided by z. So this part is the normalized probability, and so you're just averaging the magnetization of each possible configuration over all possible configurations. So that would be the expected magnetization. And how many configurations are there? There's 2 to the power n configurations, so you cannot do the sum. So this situation crops up again and again. By the way, how much time should I spend? 1.5 hours total or 1 hour total? 1 hour total. Okay, so in the next 15 minutes, I will just overview the basic sampling approach to this, because you cannot do this exhaustively. And then I maybe show a demo of a program of how it is implemented. But I'm going to describe it much more generally. So this is an example of a situation where you have a large space of configurations and you want to average some quantity over possible configurations. You want to calculate some kind of average, but you cannot do it exhaustively. So how else can you do it? You have, let's say, this is a sort of a Venn diagram. This is your total sample space, and each point here has, that's each point you can call C, has a probability P of C associated with it. This probability in this case is the Boltzmann probability, but we can be more general. It could be really any system where there's a lot of possibilities, each of them have a probability, and you want to calculate some averages over this probability. So you want to calculate some average like A sub C, P of C, summed overall C. That's the kind of problem you want to do. And you cannot do this because the space is too big and you cannot calculate all of them. So if you were to sort of intuitively look at this space, typically for the system there will be parts of this abstract space where configurations are more probable. So let's say if you can't do this, what you can do is sample 1,000 points randomly from this space, right? So let's say a bunch of points. Then I calculate P of C for these 1,000 points and calculate this number for those 1,000 points. That might work. If you pick enough points, it might even give you a reasonable answer, but the problem is that it will not be correct because this is a weighted sum with a weight P of C. Whereas what you're doing here is you're picking some points at random and you're still weighting it, but you are likely to undersample points that are not in your space. So supposing there's a very dense cluster of points here, this is the very favorable configuration, and things close by to it are also favorable. But there's, let's say, this space, there's nothing there. There's no configuration that you would even want to consider. They're all very bad. So if you just randomly pick from this space, you will end up wasting a lot of time in uninteresting areas and not enough time in the interesting areas. What you want to do is get a sample of points from the space which is actually proportional to P of C. That means that if I were to, so the probability of picking any point here should be proportional to the P of C around that point. I need not pick exactly that point, but I'll pick something nearby. So you can think of it as the real picture is some kind of continuous contour map of P of C. But what I'm doing is I'm picking points which are denser where P of C is higher and sparser where P of C is less. And then I'm calculating an average like this. And if I pick enough points, I should start getting something close to the correct answer. So that's the basic idea. So the goal is to pick some representative set of points that approximates this P of C. So how might one do that? So that's the idea of Markov Chain Monte Carlo. The Markov chain part comes from how you actually do this is you pick a point at random and then you use that point to pick another point at random and then you use that point to pick another point at random and so on. So for those not familiar with the Markov chain, it's basically a chain of things. It could be events, it could be symbols, whatever, such that the probability of the next thing, the next point here, depends only on your current state and not on the history. It doesn't matter how I came here, or where I go depends only on where I am now. That's a Markov chain. And Monte Carlo basically means land. Monte Carlo being a town famous for casinos and things. So So people came up with this idea in the 20th century at some point that maybe you can make a chain of states starting from one state, and you can have some kind of a rule such that as you pick more and more points, it will kind of converge to this distribution. What kind of rule would you have? So you want two things here. One is you want your rule to be such that you can go from any point to any other point, like you don't get stuck in some region. If I'm here, I should be able to go here in principle. Here, there should be some kind of path that takes me that way. So that's one rule in Monte Carlo. That's called ergodicity. So my moveset should be ergodic. That basically means I can go anywhere from anywhere. I don't get stuck in cycles. For example, if I have a moveset that takes me here and then here and then back here, then I'm only doing that. I'm not going anywhere. So that's not at all. So it has to be one. It has to be ergodic. And two, I want to approach the real POC if I sample enough points. So what would that look like? So the key thing here is a move, which I'm going to write it as P of C to C prime. So I have a configuration C, and I have another configuration C prime. This is my transition probability of going from C to C prime, and there is a similar thing for any possible other move I can calculate. But I want to this is my move set. This is the thing that tells me what I'm likely to do. So I'll illustrate it with that easy model in a moment, in case it's more abstract. But right now it's I want this move set to sort of converge to the real distribution, and you could say what that means is that if I have converged to that distribution and then I make this move through every point I have, I should get back the same distribution. Right? It's kind of a hand-wavy way to describe it, so I just write in what I mean. If I sum over all points in the space, what this is saying is that I take all the points in my sample, huge number of points, and then I move all of them according to this. And so I get a new distribution of points, the new places they want to. This should actually be the same distribution. So this is a condition called stationarity or general balance. So we are saying that P of C, which is the one that we want to approximate, is a stationary distribution of T. So that is what we want a T that satisfies this. But we have a problem because this again has a sum over C. That's what we want to avoid. You cannot do the sum over C, there are too many C's. So instead, what we do is something simpler, which is P of C, P of Z going to C prime is equal to P of C prime, P of C prime going to C. This is called detailed balance. And there are reasons to think that many physical systems actually obey this, but for our purposes, it is just a thing that we can enforce because this does not have any sums in it. It actually has two states, C and C prime. And we are requiring that this should be true. Now this in fact implies this, not the other way around. This does not imply, but if this is true, then try summing both sides over C. If you sum both sides over C, then this is the left hand side. And on the right hand side, there is no sum over C prime. You're summing only this term over C, but C prime has to go somewhere, so this sum is 1. So you get back to C prime. So this implies this, but not the other way around, but this you can enforce. So those are the two conditions that you need in MCMC sampling. If you have a move set that satisfies ergodicity and detailed balance, then the idea is that you start from any state and keep on moving according to that move set, then eventually you will fill up the space in the way you want and you can calculate these averages and so on. So just to take a concrete example, what do you mean by a move set? So let's say you take a spin system and you have started it up with everything up, that's your initial state, or in some random state that will only be better. Now this is your C. What can C prime be? It could really be anything, but you don't want it to be anything. You want it to be constrained somehow. So typically a possible move you do in these systems is you pick a random spin. Let's say this one, and then flip it. And that's the C prime. So it's clear that this kind of move satisfies the modicity that by picking random spins and flipping them, I can eventually reach any state in the space. We also need to satisfy detail balance. And there are many ways to satisfy that. I'm going to give you two ways in this case. So I'm just going to write down the formulas. Similarly, this will imply that P of C prime going to C is equal to P of C divided by the same denominator. So you are dealing with only two states here. So this is a case where you are picking one spin and flipping it, and so those are two states, the first state and the second state. And your transition probabilities are given by this. Does that satisfy detail balance? So you plug in those formulas here. So it's going to be P of C times this, and this will be P of C prime times this, and they are equal. So this satisfies detail balance. So if you simulate a system, a spin system with this rule, and remember for the spin system, the P's are given by the Boltzmann properties. So you just have to calculate the energy difference when you flip the spin, and you can do that. This is not actually done. There's something even simpler which is done, which is called Metropolis. After the person who came up with it. What I wrote about was a version of Gibbs sampling. It is never used for exploring just two states, but it is used when you are exploring more than two states. I might come to that, but I don't think at that time. The Metropolis sampling is used when you have this just two states, C and C prime. P of C going to C prime is equal to 1 if P of C prime is less than greater than P of C, and is equal to P of C prime divided by P of C otherwise. What that means is I flip a spin and I calculate the new probability, the new energy, therefore the new probability. If I get a better state, lower energy or higher probable state, I accept always. But if I get a worse state, I still accept with this probability. So if it's a worse state, then this is a number that is less than 1, and I accept it with this probability. Does this work? So let's plug it into that detailed balance equation. Supposing P of C is in fact greater than P of C prime, then the left hand side will become P of C times P of C prime divided by P of C. The right hand side, this is flipped out, so this will be 1 because C is more prominent than C prime. So you get P of C prime. So you have P of C prime on the left and on the right, it works. Similarly, if it's the other way around, I get it. Why do this and not this? Any ideas? All of them are correct. So it's just that you have to do this hundreds of thousands of times, millions of times for a reasonable simulation. So you are not able to explore this exponentially large space, but you still want to explore as much of it as you can. So a typical simulation takes a long time. Now, how many calculations do you need to make for each step here? You will need to make one addition and one floating point division. Whereas here, if you're accepting there are no calculations to be made, if you're rejecting it, it's just one division, no addition. So that kind of small efficiency really adds up when you simulate. So this is the standard way to simulate this kind of a spin system. So I have a sort of demo of actually doing this. Okay, so I do a 1D model here. You can also have a 2D easing model and a 3D easing model, and you can have models of various different lattices. So let's say you have a 2D model, then your Hamiltonian will look like slightly more complicated, but let's say it's in a square lattice. You can simply write the Hamiltonian as the summation of is j with this notation ij, which is usually used to indicate nearest neighbors. So that means is that you are summing for all pairs of spins that are nearest neighbors. So I'll draw the links here. You're basically summing for spins that are linked from these points. And then if you want to calculate something like the magnetization, you just simulate using this rule at any given temperature. You can calculate the expected magnetization at that temperature, and then you can plot the results. So this particular model, the easing model, it turns out that it can be solved exactly in both one dimension and in two dimensions of the square. And it is known that the 1D easing model does not have a phase transition. So you will never start making a magnet with the one-dimensional model, but the two-dimensional model does have a phase transition into a magnetically ordered state. So as you reduce the temperature, at some point it starts getting magnetized. And at zero temperature it's fully magnetized. Both of them are fully magnetized at zero, but in one dimension at any finite temperature it's not magnetized. So we are past 3 o'clock. I was going to talk about another application and something called flip sampling that is more widely used in bioinformatics, but I don't think I can do justice to that. But if you like, I can quickly show you some Jupyter notebook with an implementation of this. And if you have any questions. These functions, I don't actually need them, but I wrote them anyway. So here the configuration is just an array of numbers +1 or -1, and this calculates the energy for a 1D chain. It is just j times the nearest neighbor sums. And I'm using what's called periodic boundary conditions, which means that after n comes back 1. So it's like a circle, not like a linear line. And in 2 dimensions, I have 2 sums over the 2 dimensions. And so nearest neighbors in this direction and also in this direction. And again, the periodic boundary condition. So if I go beyond n, or if I go beyond L and m, I get back to 1. So those are the Hamiltonians. And And the magnetization is just the sum of all the plus ones and minus ones there, times some number, but we'll ignore that. We're just calculating this as the magnetization. So that's the system, and what we need to do is calculate. So the algorithm is you pick a random spin and etc. So this function calculates for a 1D system. It picks the random spin and the energy difference when you just flip it, and it returns that energy difference. So let's just go back to the math here. So let's say you have a configuration E of C1, and that is associated with the probability. So this is the probability of the first configuration, and P of C2 will be equal to what we require for Metropolis, or even for this, is not the probability but just the ratio. So you don't actually have to calculate Z, which anyway you can't calculate. You just have to divide. You have to see whether this ratio P of C2 by C1 is greater than 1 or less than 1. Just call that CNC time we can show you here. This is CNC time. So P of C prime divided by P of C is simply going to be equal to e to the minus E of C prime minus E of C. No Z here, it is only this. And this itself is simple to calculate because you're only flipping a single spin. So let's take the 1D case. And let's say you choose to flip this spin. This is your one that you flip. What is the change in energy? All of these interactions stay the same. Only these two interactions change. So in your initial state, this was a +1 and this is a -1. In your next state, this will become a -1, this will be a +1. So the change will actually be 0. Or if you flip this spin, this is +1 +1. If you flip it, it will become -1 -1. Either way, it is just 2 times the difference. So each of these, when you flip it, it just changes sign. So when you're subtracting over here, it is just 2 times the initial. So that's basically what's implemented here. This is the interaction between the 2 spins on the left and on the right, and it is -2 times. That is the change in the energy. Then return the change in the energy. So this function flips a single spin and returns the location of the spin and the change in energy for a given configuration. While the language is a language called Julia, and if you don't know it, it doesn't matter. It's fairly easy to read. This is the same thing in 2 dimensions. And now you can calculate the average magnetization at any temperature. So the input for this temperature is, this function is the temperature, and the value of J is it current magnetic, whatever, and the current configuration, and the number of iterations, which is how many times do I want to sample this space. So I want to calculate the average magnetization by taking a large number of samples, 10,000, 100,000, and averaging the magnetization over there. So this is the initial magnetization counter, and typically when you start a Monte Carlo simulation, you throw away the first so many samples because you call it equilibrating. Your initial choice is not likely to be very random. Maybe you just took a uniform thing. So you let it run for a while and don't consider it, and after you call it equilibrated, then you start doing it. So if I'm giving 10,000 iterations, I will throw away the first 2,000. This stuff is, for 1D systems I'm calling this function. For 2D systems I'm calling this function, but it's basically the same thing. So I'm calculating the energy difference If the energy difference is negative, that means I'm going to a more probable state and I'm accepting it. So I'm making this move. If it is positive, then I'm calculating this ratio and comparing it to the random number. And if the random number is less than that, then I'm accepting it. So that's exactly the Markov move. Similarly, if it was a 2D system. And then if I have exceeded the number of equilibrium runs, then I am adding the total magnetization to this, and then finally I'm returning and divided by the number of runs I actually calculated. So that's all there is. And my initial configuration for a 1D system is just an array of ones, 10,000 elements of ones. And then my temperature is, so this is some Boolean, but what I will do is temperature is this, it's from 5 to 0.1 in equal steps. And then this is the magnetization. I'm just calculating the average magnetization for every temperature in this list. It'll take a couple of seconds to run, but anyway, I've run it before. And yeah, so this is the array, and I can plot it. If I plot it, I don't see much. So you see that I had 10,000 spins. And I get some fluctuation of the magnetization, which increases as you increase temperature, but there is no like, it's like minus 200, which is of the order of square root of 10,000. It's not much different from random. So that's what you get for a 1D system. For a 2D system, so let's say this is now a 2D system with 20 by 20 spins. It's not a very large system, but still you can run it efficiently. And I do exactly the same thing. I same temperature range and same calculation for magnetization. Now you see that at low temperatures you are getting a magnetization of 400, which means all the spins are pointing in the same direction. And if you plot it, so this is a little bit of noise you can ignore. But at high temperatures there's basically no magnetization, and then you pick up a magnetization. So I think this is just an artifact that it started magnetizing this way and stochastically the other way, and then it magnetizes. So this is kind of known, and this is a very toy example. As I said, this is an exactly solvable problem, but many such problems are not, including if you do this on 3D, it's not solvable. In 2D, with an external field also, I think it's not solvable. And even this basics kind of system, you can learn more. So this is magnetization, but you can also calculate just the average energy and then the specific heat by differentiating it. And so I should probably stop here, but my PhD work was actually, a chunk of it was an Ising model and a simulation very much like this, but the lattice was something complicated. It's called a pyrochlore lattice, and it's basically a lattice of corner sharing tetrahedra. And these were actually discovered in some experimental compounds called radioactive titanates, and they were actually, the Ising model is a very good model for those. And the lattice looks something like this, that there's a lattice of corner sharing tetrahedra. It's all but it's in 3D. I won't like to draw it in too much detail. And the spins are on the corners of these tetrahedra, and they actually, the direction is like pointing in or pointing out, but we know that let's say it's just out. But there is in spins, they are plus 1 or minus 2. Now on a tetrahedron, and these are antiferromagnets. So on a single tetrahedron, what is the ground state? There are 4 spins, and they're all talking to each other. 4 spins, and they are all linked. So if you think about it, 2 spins up and 2 spins down is the best solution. But there are how many ways can you have 2 spins up and 2 spins down? There are 4 of them. You can have OC2, which is equal to 6 possible configurations of having 2 spins up and 2 spins down. And out of 16 possible configurations, which is 2 or 4. So it turns out that in the full system can satisfy the ground states for these tetrahedra. via a macroscopic number of computations. That means so I mentioned 2 laws of thermodynamics. There is a third law that is sometimes quoted which says that as you approach absolute zero, the entropy of the system goes to zero. In these systems, that's not true. And some of you might know that the normal state of ice, water ice, also has a finite entropy at the ground state. And that was discovered by Paul in the 30s for a very similar reason. So ice is made of water molecules, and it has a tetrahedral structure where each oxygen has 4 neighbors arranged in corners of tetrahedron. And each oxygen is part of a water molecule, so there are 2 hydrogen atoms. And in the ground state, the hydrogen atoms should be arranged in such a way that 2 are near the oxygen and 2 are away. So again, there is that combinatorial thing that you have 6 ways of arranging the hydrogen atoms near each oxygen atom. And so water does not converge to an ordered ground state. If you look at the hydrogen atoms, it has a ground state with finite entropy as you face it. So this is ice, and those systems were called spin ice and became quite a topic of research. I believe people are still working on it because looking at that area for a while. So yes, with that I'll stop here, and would like to get some questions, or you can come and behind you on, you can talk to me.
So, sir, I have a pair of questions.
Yes.
So, first thing, when we are moving from seed coin to the next point, like C to C planet,
Yeah.
then you are choosing randomly finding out a point and flipping the
Yes.
spin.
Yes.
Would there be any other way of doing the similar thing while maintaining the Markov chain properties or some choice of proposals?
Okay, describe it as Markov chain. It doesn't matter what you do, but convertibility, which is what I mentioned. You need to be very careful that you should be able to reach any state from the state you're starting. So you could think of a system where instead of randomly making a spin and going from left to right, flipping this and then this and this. That actually is also robotics, but it's less efficient usually.
And second thing is about this particular, let's say, starting a chain of number with very large number, like with a very large number of steps. Would you suggest to run a single chain for the convergence, or would you suggest to start with multiple walkers or
That's a good question.
how would we check whether it's converging properly or not?
Yeah, so this is actually a very sophisticated field. This is a really productive. There's something similar to this that people actually do for meta-convergence problems. So this, you can prove that you have convergence in infinite time, the global is infinite time. So for any given problem, there are different ways to make it converge faster. And now this parallel chains, people actually, the other convergence problem is when you lower the temperature, it tends to get stuck in better stable states. So there's a technique called parallel tempering where they run multiple chains at different temperatures, and they also have some exchange mechanism between the different chains. And that turns out to improve convergence at low temperatures. So there are a lot of such things.
And to figure out the burnout space, we just figure out where it is converging, or like randomly choose the numbers.
Yeah, here I just randomly choose, but then if you're doing this seriously, you should have some estimates of how much. Anybody else?
So, why on earth is the law of large numbers?
Why does the law? Can I say the law of
I mean, in the context of which I'm saying is that take a large number of samples and then take it to the populating in the real time. There's no reason that would happen.
Yes, so I didn't really talk about the connection between entropy and so on. One way to think about it is you could take a large number of samples and they're all 10. But if you're picking a number from 1 to 10, or let's say you're rolling a die and you're calculating the average of the roll, you take a what is the average number you expect from rolling a die You would say it's 3.5, but let's say you don't know that, you're going to calculate it. And you roll the dice 100 times. And now it is possible that all of the 100 rolls are 6. And then you'll get an average of 6. Or it's possible that there is some bias and instead of 3.5, you get 4.5. So then you can basically ask for, so then your microstate is its actual sequence of rolls you get. The macrostate is the average number that you are seeing. And then you can ask, what is the, how many microstates correspond to your macrostate? That means in how many ways can you get an average of 3.5 with 100 rows? How many ways can you get an average of 4.5 with 100 rows or 4? You'll find that it's actually, if you calculate it, it will be a very, very sharply weak distribution. So, though any possible average can come out from these rows, most of the microstates in your system will be an average of 3.5. With most meaning you can basically find everything else. So that's kind of an scientific explanation. And if you're familiar with things like Lagrange multipliers and constraint optimization, you can work it out. You can actually work out the formula for it. Yes, I can do that for you. Did that answer the question? So basically, the average is overrepresented in the possible computation. But you can also ask how will it different. So let's talk about coin tossing and let's say how many hits do you get in 100%. The average is 50. But you won't get 50, you might get 55, you might get 48. But you probably won't get 70 out of it. If you get 70, then you'll think there's something wrong with the coin. And but you 55 might be not surprising. But if you toss a coin 1,000 times, then 550 might still be a little surprising. 600 will be very surprising. So what's the difference of the average that you expect? So you might have done those things at home. So if the average is goes as an final deviation to the square root of it. Okay. Thanks everyone.
Thank you, sir, for coming to our college to give this wonderful lecture, and also thank you for everyone who attended. I would like to call Dr. Akshay to present a small memento to Dr. Rahul. Thank you everyone, and thank you to Dr. Rahul once again. I would like to ask everyone to kindly join us outside for refreshments. And if you have any sort of questions, feel free to ask. Thank you.
Also, we have a small photograph and then we can